is that, yeah.
So the sigma mu nu at the top there.
This guy?
Right. And then on the right, you just have a regular Pauli matrix.
This is regular Pauli matrix. And how do I do that? Yeah. I've gone to 2 dimensions because one writes Dirac in Dirac basis, something that I really fuzzed over. There's a long song and dance that in non-relativistic limit, this guy is significant and the other one is not. So it's really equation for the spinor, 2-dimensional spinor. So that's why there's an error here, I guess.
What is chi? Can you just write?
Yeah, the 4-dimensional spinor in Dirac basis can be written as composition of 2 spinors.
Right. Okay.
2-dimensional. And then, there is physics that are omitted in our discussion of Dirac representation, which is that you can interpret this in relativistic mechanics as the spin of electron, and this guy goes away. Because as you remember, the Dirac equation written on these 2 components showed up with plus and minus sign, and only one of them was the one that you care about in non-relativistic limit. But I agree I didn't do that in sufficient detail. But now I can, summarize what Dirac got allegedly on the 2nd day after deriving his equation, because he first went to sleep. So the legend is that he went to sleep because he was afraid it wouldn't work out, and the equation was too beautiful to give up on it. So he didn't do it the same day. He did it the next day, and it came out correctly. So this calculation that we are doing. So, to put all the details in non-relativistic limit, Dirac goes to Pauli, then there is minus 2i m ddt minus that, because we were looking at time-independent equation. Now we can go back to the time-dependent Schrodinger, stick with time dependence. So, so this is just the usual 3-dimensional Laplacian. Then there is this part, but then there is plus 2s and that's acting on the did I erase it again? Well, one of the 2 spinor fields, whatever it was. Phi. So this is 2D spinor. So this is the non-relativistic. And this was a big puzzle in experimental atomic physics because they observed that factor of 2 already. They saw it in hyperfine structure, etc., very accurately. So it was there, and that was, a big puzzle about all quantum mechanics. Where does this come from? So this is Dirac's triumph. So, 2 things happened with Dirac. First, he explained an experimental fact that non-relativistic quantum field theory did not succeed. And there are also attempts of adding relativistic corrections. So, for example, Sommerfeld, if I remember this correctly, added the first relativistic term, just expanding the, in powers of c squared, and didn't get that term. So this extra 2 was a big thing, number 1. And then, of course, the number 2 is a prediction of positron. Now, about that, he was much more tentative, even though today that's what we remember. This was an experimental fact. Now, nobody wanted positron at that time. The theory then assumed that the positron was actually the nucleus. When we're trying to understand how the atom was put together, it's only the discovery of neutron spoiled that kind of way of thinking. So this is not quantum field theory, but it's very good relativistic quantum physics. And the curious fact is that we will now explain that quantum field theory brings a correction to this effect, and that was also measured in experiments. So it turned out that this factor 2, went away in about on a level of 1 part in 1,000. So they measured the spin and orbital magnetic moment in hyperfine splitting, and it wasn't 2, it was very close to 2, but it was away by 2, and the Schwinger's triumph was to explain what the effect of quantum field theory on this. But before I do this, I would like to instead of using this argument, go through another version of it. So what we have done here, we somehow connected it to Klein-Gordon equation. But one can actually just work on the level of the Dirac equation and obtain the same result. That's one reason I'll do it. The other reason that was very surprising, and it took young generation to fix it. It turns out that calculation of the first correction to magnetic moment is actually most conveniently done in a covariant or relativistic gauge, which is kind of surprising because this whole argument is that you're looking at rest frame, etc. But the calculation likes that thing better. So I would like to repeat this in a covariant way. I'll give you another identity which has the same result. But it's useful in covariant calculations. And that's called, and I forget if it's Gordon or Gordon. Let's say it's called Gordon decomposition. This could be A. So it's just a very simple identity, but it's very convenient. When we are looking at the vertex of electron in, electron out, and the photon interacting, we discussed it last time, then we are looking at something that is sandwiched between electron in, electron out, and here I'll stick something not very well motivated here. So this momentum, gamma mu, plus this momentum here. Now, Dirac equation says I can replace this by mass because I'm on the mass shell, and I can replace this by mass because I'm on the mass shell. And remember, these U's show up rather than size because we're in momentum space rather than in configuration space. So far, we were only working in configuration space in all this. So look at this. So this becomes M, this becomes N. So this is twice the mass, U slash P prime, gamma mu UP. And if you remember, this is the form that the vertex took for coupling of let's say positron, electron, and a gamma mu, or electron in, electron out, and vector potential, of electromagnetic vector potential. So that's, trivial identity, but here we can use the commutator, the anti-commutator, because we can write this as P nu prime gamma nu plus P mu gamma mu. And this guy is the same thing as G mu nu minus the symmetric part is G mu nu, and the antisymmetric part is minus I sigma mu nu, which is, we understood this as being the magnetic moment, because that'll be the Pauli matrices that lead to the magnetic moment. So now I can use this identity, so that equation up here becomes u bar p prime p prime plus from here plus p mu and I'll put this 2m on this side, so it's over 2m plus which is just the vertex modulo IE, etc. But the vertex Feynman diagram for the vertex, Feynman rule for the vertex P prime out, P in. So this thing can be interpreted as something that you would also see for boson fields. So this can be interpreted as something that a charged scalar field would also see. But this is, spin magnetic moment. Part. So the reason why this is of interest is that when you actually try to find all the tensors that you can write, the list is very short. I mean, the tensors with one index, when you have these, you have p's, and then you have the difference between the p's, p minus p, we called it q, because as we went into the vertex, this was p, this was p prime, and this was q coming in, and the momentum was conserved. So you have, two momenta at your hand as the 4 vectors. Then you can compose the momenta with the sigma mu nu, and that's about it. So if you want to understand what the vertex factor, so this is what the bare vertex factor looks like. I can write it this way, or I can write it in terms of available tensors, in terms of momentum and gamma matrices. And now you can ask yourself, what is our one particle irreducible effective thing, which which we discussed before, which means I allow anything to happen. So I prepare an electron, and I prepare a photon, they interact, but then all the corrections of the quantum field theory come in, the ones that we discussed when we defined the Gibbs free energy, etc., the effective vertex, and then we go out. So, what form can disk have? And on the general principles of just constructing things from available invariant tensors times the scalars, the most general form this thing can have is, so I'm supposed to put an IE someplace, because our vertex came with, did I bring the final rules with me? Yeah. So this thing came, this came with plus IE, this vertex, multiply both sides by electron coupling and an IE. And the most general thing that the full quantum field theory does with all the corrections, this is just the bare term, has a very simple form. It has to look like a tensor of this kind. So it'll be, well, actually no, a tensor of this kind, gamma mu. You people. Gamma mu with some function which is in perturbation theory the sum of all the Feynman diagrams that we know how to generate. And then there is the second term, sigma mu nu to m. And this thing is just the photon momentum, this difference. So there is a q mu F2 q square. So because the momenta evaluated on mass shell, there is no dependence on the momenta. The only dependence is on the form momentum transported to the vertex by the photon. So that's just a definition, these Fs. These things are called form factors. And you won't see them only in quantum field theory, you also see them in condensed matter physics when you use it, doing field theory there. So it says that all the corrections show up to this vertex. This is what we call charge renormalization. It will be the effect of all corrections to the charge. And then there is an effect, all corrections to the magnetic moment, F2. We can use the Gordon decomposition. So you can use this identity to replace the first term by momenta. That's an identity, right? So one particle irreducible, free vertex in quantum in QED. can also be written as UP prime. P prime plus P over 2m. But if you use a Gordon decomposition and replace it by p's, then we'll get an extra contribution to this term. So another way of writing the same identity is sigma mu nu mu 2m so this term also contributes just because of the identity. Sorry. F1 q square plus F2 q square UP. And now something happens that, I don't know, maybe if you have some time in December, which is not very much time, but if you have a few lectures left, there's a big piece of very important physics which I haven't discussed at all, which is renormalization. By convention, what we mean by IE, we mean that the product of bare E times all the corrections, F1, as Q goes to 0, so F at 0. This is the observed strength of electromagnetic coupling. So by definition, if we write this in terms of what we observe as strength of a field, because we have no access to the bare coupling at all, the only thing we see in the lab is always the electron plus its all corrections, all its virtual field that surrounds it. That's the only thing we see. Then this becomes, in terms of observed electromagnetic coupling, this becomes, by definition, P mu prime plus P mu over 2m times 1 plus I sigma mu nu over 2m Q nu, the momentum that's impacted, times 1 plus and I have to explain why 0 is showing up in this experiment, in which you have a jar with very good vacuum and electron moving in weak magnetic field for months. The momentum transported is 0 because it's very weak. There is no real kick. So this is the weak magnetic field limit, and this quantity should I have it here? I guess let's put a tilde on it. You're correct. I mean, it actually shows up in that way in calculation, but we won't see this in the first order. You know, when you compute Schwinger correction, there'll be a order alpha, and we won't see the wave function renormalization or the charge renormalization in that. So this quantity F2 of 0 is called the anomalous electromagnetic moment. And you know, if you read on the course home pages my rant about gauge invariance and why it's a pain, I actually have a link to Schwinger's original article. Now this is totally scary because it's physical review. They didn't have physical review letters in 1948 because there was no need. It was a very thin journal. And it has a half-page article by Schwinger and says blah, 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 and the answer is alpha over 2 pi. So, you know, how anybody would actually reproduce Schwinger's calculation from that Fizerev letter, I can't even start dreaming about it. It's a totally amazing article. And the horrible thing happened in Japan at the same time because Tomonaga's student did the same calculation and he got a factor of 1/2 wrong. So he had to shave his head in shame. So he went around with shaven head because he screwed up. You know, they got the letter. The Fizerev arrived by, you know, ship from United States. Tomonaga saw it and they were off by a factor 1/2, which was a disaster for Japan. So now that's what we will do next time. Start doing it because it turns out even this very simplest calculation you can do, you know, takes number of tricks. Now the Schwinger was very lucky, or you know, he chose his problem very well. It was a very physical problem because experiments were in disagreement with Dirac theory. That was well known. So and Schwinger, you know, just like Dirac got factor of 2, Schwinger got the answer correct to 6 decimal places just by thinking. So that was, you know, the first triumph of real quantum field theory. There were some other, you know, proto-triumph. Hans Bethe computed lump shift, etc. But that was all done by the seat of their pants. The Schwinger calculation was really the first honest quantum field relativistic calculations. So the Schwinger correction So Schwinger was one of these people that, you know, we have a number of in the history of science, and like Hamilton was something like that. But anyway, you know, at 16 he showed up at Columbia and talked to Rabi, who was, you know, probably the best American physicist at the time, or best experimentalist certainly. But then the war happened, so then he was working in radiation lab at MIT, designing radars. So it was a very important part of the war in Atlantic and Pacific. And so he was very old. He was maybe 19 or 20 or something when he did this, because there was this interruption. But he could have done it even earlier. On the other hand, it's not clear because the war was very good in disciplining minds of theorists. So these young theorists really did very hard work during the war. You know, Feynman worked very hard, and Schwinger worked very hard, and Dyson, they all worked very hard on real engineering problems, like, you know, how to kill very many people at one time. At least Schwinger was, you know, more defensive. He was defending the So perturbation series, sorry that I petered out there, but it's irrelevant. Perturbation series starts with the bare vertex. And then it has a series of diagrams, of which I'll draw only once, which was Schwinger's good luck. Because if it wasn't for that, it would be more painful. There's a diagram like this. You know, classical or on-mass shell electron comes in, gets kicked by a photon, and propagates to be an on-mass shell outgoing electron. And in the meantime, it absorbs, reabsorbs the photon. So that's the real calculation. But it turns out that one has to be included when you're computing F1, the charge. It has to do with, it can be interpreted, it has to do with reinterpretation of the mass of electron, its wave function and how it joins. And there is, of course, the other guy like that. But it turns out for magnetic moment, they're not important. And as an incredible piece of luck for him, as we'll see, this contribution is finite. So there is nothing to it. You just have to do a calculation and compute it. Now, people already knew since 30s that there was a problem with quantum field theory, and that's the reason why I gave it up. So various people, maybe Oppenheimer contributed something, and Weishaupt and various people before the war. They knew that theory is beset by divergences. And all other calculations, perturbator calculation, require careful think about what these divergences mean, and that was only done by Dyson and maybe by Salam later. Salam got a Nobel Prize, Dyson didn't, but Salam sent color televisions to a Nobel committee, and Dyson didn't. Or I don't know, let's say that he cultivated Nobel committee. It's one of the things, there's all kinds of people showing up in Sweden for no obvious reason at all, and they're being very friendly to certain Swedish physicists. So Salam was one of those. Anyway, we will remove this from the recorded sequence. So it turned out that Schwinger only had to compute a diagram like the one that we talked about last time. And, so let's call this diagram gamma mu. And where gamma mu is, so there'll be one momentum flowing unconstrained inside, because this photon can have an arbitrary energy. And so there'll be one integral we'll have to do to sum up overall internal energy states. So now they call it delta from k over 2 pi 4. And then this photon carries minus I over k squared. So there'll be P going in here. We'll set Q go to 0. So the external momentum will be very weak because we're in this very non-relativistic limit. So P comes in, P prime comes out, which will be, for all practical purposes, P. Then the K goes this way, so here we have momentum K plus P, K plus P, and da-da-da. So here is the photon part, very simple. And then there is an I, epsilon, gamma mu, so this has the vertex And this gets summed because we are using a Feynman gauge where there is in propagator there is g mu nu, so this index will be also mu. And this one will have another color, and then there will be this propagation here, which is p slash plus k slash minus m gamma mu, and these guys carry i's with them, and this IE is from the 3 vertex, this one there, and mu, call this mu, okay, I over p slash plus k slash minus m gamma mu, boom. So that's the Feynman diagram for this vertex. Now, as written, this Feynman diagram contributes both to the F0 part, F1 part, which I erased here, well, this guy, F1, and F2. So if you study an honest book on quantum field theory, all this stuff has to be worked out in great detail. So that is. But we will only concentrate on the contribution to the sigma mu nu part, which we know that has to do with changing the strength of magnetic coupling of the spin. And there is a trouble, which was obvious already in the 30s, and it can be done by power counting. So if you look at this integral, k can be arbitrarily large. So when k